It's a series where where the terms change signs alternatively. Right? Meaning, if the first one is positive, then you have negative, positive, negative, positive, negative, so on. Okay? So in general, you have -1 to the n minus 1, in this case, a to the n. So if an itself is bigger than or equal to 0, then all you have to do, put a -1 to the n, for example, a sub n, and starting from 0 to infinity is an alternating series. Okay. Okay. For example, one example: 1 minus half plus 1/3 minus quarter plus 1/5 minus, and so on, which we can show it by -1 to the n minus 1 over n, and starting from 1 to infinity. That's an alternating series. Now, for each alternating series, if you consider the series with all positive terms, it's called the absolute value series. Right? It makes sense. All you have to do, let me write down a couple more examples. Well, let me define it here. If -1 to the n, a sub n, and starting from 0 to infinity is an alternating series, then the sum of a sub n which is basically the sum of absolute value of -1 to the n a sub n, and from 0 to infinity. All you have to do is just drop that -1 to the n. Just consider all the positive terms. Is called the absolute value series. Right? So, for example, for the one we started as a first example, what's the absolute value series? The absolute value series is simply sum of 1 over n, right? Which is 1 plus 1/2 plus 1/3 plus so on. Let's do more examples. Question: the series that I'm about to write, is this one alternating? Hello? Is it alternating? What makes it alternating? Yeah, the cosine part. It's n pi, right? So it's 1 minus 1, 1 minus 1. So in fact, we said cosine of n pi is exactly -1 to the n, n squared, n from 0 to infinity. N should be from 1. Sorry, guys. 1. And as you can see, this is -1 plus 1/4, -1/8 plus 1/16. What am I doing? It's not 2 to the n, it's n squared. So it's 4th, 9, 16, right? And so on. Now, let's go back to the first example. Consider this guy and consider this guy. What do we know about the behavior of the left one? Does it converge or does it diverge? And why? P series and it diverges. Right, that's P series with P equal 1, right? P equal 1. P series diverges. What do you think the behavior of this one is? You don't have to explain why, just make a guess. You think it converges or diverges? Do you think it diverges too? Would you be surprised if it converges? No? Okay, then it converges. Is anybody surprised that this guy converges? Like when you alternatively subtract terms from this one, it converges, right? On the left one, you keep adding terms to it. You keep adding values. Here, you start with 1. Let's make this -1 so we can start with the positive. So it's 1 minus half. Then you add 1/3, but you subtract 1/4. You add 1/5, you subtract 1/6, and so on. And then converges. Okay. The reason for this one is, for this one specifically, we can, talk about what happens to the terms. Think about it. Let me write it here. So it's 1 minus half plus 1/3 minus 1/4. Okay. Come on. 1/4 plus 1/5 minus 1/6. Let's write down even the next one. 1/7 minus 1/8. Okay. Consider each pair. What's the subtraction? That one is half. What's the next one? The next one is 1/12, right? And let me go ahead and write the denominator as 3 times 4. The next one is what is the next one? It's 1/5 times 6. The one after that is 1/7 times 8, and so on. So somewhere in the middle, you have 1/n times n plus 1 squared. Okay. But what we care about is that 1/12. Do you guys agree that 1/12 is bigger than 1/16? right? Because when denominator gets bigger, the fraction is smaller, right? The next one is, smaller, bigger than, let me do it this way. So this is larger than 1 over 16. That one is larger than 1 over 36. That one is larger than 1 over 64. 36, what am I doing? Plus, and that one is larger than 1 over n plus 1 squared. Agree? Okay. Now, and this one is, let's write this one. And this one is bigger than 1/4. How about that? So you can see the pattern. Okay. Now, what series is this compared to? In fact, you have 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared plus. You have all the even numbers. Okay. So, you don't have to write that. Oh, come on. So what is that? That can be written as sum of 1 over 2n squared and from 1 to infinity. Now, if you FOIL that, it's 1 over 4th, 1 over 4th, and then sum of 1 over n squared, and from 1 to infinity. So this is what we got. It started with negative 1 to the n. Hold on a second. I wanted to say this converges, so it shouldn't be bigger. It should be smaller. Damn it. Well, all I have to do. So I have to do an adjustment, guys. I have to erase all of that. And I have to change all the denominators. So I wanted to show this as a smaller. So that's 9. That's 25. That's 49. And that one's 1. Okay? And then all of these denominators change to 1 square, 3 square, 5 squared, 7 square. So this one right here should be 2n plus 1 squared and starting from 0. Okay, that's better. But we can do what we were about to do here. I can just expand it. So this is 1 over, 4n squared plus 4n plus 1, and starting from 0 to infinity. Okay, so we can say this one. So we got negative 1 over raised to n minus 1 over n. So we proved is less than equal 1 over 4n squared plus 4n plus 1. And starting from 0 to infinity. Same thing, and starting here and starting from 1 to infinity. Now, so this is a smaller. What do you mean about the bigger one? Does it converge or diverge? Do you think the one on the right diverges or converges? converges, and it's in fact comparable with, you could do integral test, okay, and it becomes a tan inverse if you want to do that. And also, well, it doesn't even become tan inverse, it's just a natural log. Well, it's -1/, sorry. It converges, or you can compare it with 1/4n square, this one, limit comparison. But this one converges, that one converges as well. So the bigger one converges, that means the smaller one converges as well. Thus, this sum converges as well. Okay. So that one was just an example that when you change the signs of a divergent series to positive, negative, it might converge. Only it might, okay? You don't have to prove this for every single series. So that's the theorem. It's called alternating series test. And it's very simple. Consider, well, not even that. For a given alternating series, sum of -1 to the n, a sub n starting from 0 to infinity. If, that's all the condition you need. By the way, we are assuming that a n is bigger than or equal to 0, right? If a n approaches 0, let me write it in terms of limit. If the limit of a n approaching infinity is 0, then the alternating series converges. That's it. Then sigma converges. At the beginning might be very confusing. Let me explain. Let's go back to the example again. So consider the absolute value one, right? Which was sum of 1/n and starting from 1 to infinity. The alternating one is this guy. Okay. In fact, let me write it this way. -1 to the n minus 1 times 1/n. Okay. So if you compare this structure with the top one, this is the a sub n in that setup. So the right one, you look at it, and so it diverges, right? Because it's a p-series. Also, up to this point, every time we took limit of an, and if an goes to 0, it's inconclusive, and term is inconclusive. But if it's an alternating series, this is enough for the entire series just because of that scalar, right? Just because of that alternating factor, alternating coefficient, whatever you want to call it. The number that causes this series alternating, terms alternating. The only condition you need is this guy. I mean, it's a very easy test in the case of alternating series. So only check this guy. And if that happens, if this happens, then the -1 to the n minus 1 a sub n converges. Okay? But that's a necessary condition. Now, a lot of series that diverged so far, all of a sudden they're going to converge. Okay. Let's go to the example that we just did in the quiz. The 2n over n squared plus 1, and from 0 to infinity. We showed this one diverges, although an goes to 0. Now, this series, this one, negative 1 to the n, times 2n over n squared plus 1, and from 0 to infinity, converges. And this is justification. You say because it's an alternating series with an approaching zeros. That's it. Alternating series with an approaching 0. Okay. Let's do a couple examples. There's one more thing in 10.7. I'll talk about it on Thursday. 10.7. It's called basically the absolute convergency and conditional convergency. This is part E, number 1. So that's the sum of negative 1 to the n over n plus square root of n plus 100 as n starting from 1 to infinity. Okay, let me rewrite this in a way we can see what an is. So this piece is a sub n, and that's the alternating coefficient. So anytime you see negative 1 to the n, can you assume it converges? No. Example. We need the condition that this guy approaching 0. Does that approach to 0? No. So this one diverges. So I'm glad you asked that question. So here, an equals n over n plus 1 does not converge to 0. Thus, diverges. So it depends, if it's alternating series, all you have to do is check this guy. See if it converges, goes to 0, approaches 0, not at infinity. Okay. So let's go with this example. So it's an alternating series, right? So this is how you justify it. This is an alternating series. And 1 over root n plus 100, does it approach 0? Does it converge to 0? Yeah. As it goes to infinity. And you can see, you have constant dividing by infinity, so that it eventually approaches 0. Thus, this series converges. If not, does it just diverge? Yeah. If the an doesn't go to 0, in fact, it's the nth term test, right? The fact that if an doesn't go to 0, if you multiply by negative 1 to the n an, that one doesn't go to 0 either. right? Because think about it. Eventually, it's going to be either -1 or 1. 1, -1, this entire thing. But what matters is that doesn't go to 0. So by nth term test, diverges. Okay. Let me see if I can add something to the theorem. So theorem, it says alternating series for then it converges. So here I can say, and if an doesn't convert to 0, then the sum of -1 to the n a sub n diverges. Okay. All right, we can stop here. The questions are simple, doable. So if we look at questions on 10.7, they're asking, do they converge absolutely or conditionally? Let me quickly mention that. For an alternating series, -1 to the n a n. The absolute value series, the absolute value series, which is this one. I'll have to say if. For an alternating series, if the absolute value series, this one, converges, then we say the sum of -1 to the n. The original one converges absolutely. But if the absolute value one diverges and the alternating one converges, then we say this guy converges conditionally. I'll explain it quickly by an example. Consider these two alternating series, this one and these two. Okay, so these are both alternating. Question for you. What's the absolute value series of this one? The absolute value series. Drop the -1 to the n, right? So we're going to have 1 over n squared, and starting from 1 to infinity. Question. Does the absolute value series, which is sigma 1 over n squared, does it converge or diverge? Hello? Converge. Why is that? P series P equal to, right? That's it. P series P equal to converges. Since this happens, remember, in general, I should have mentioned this. Always, the alternating series is less than equal the absolute value one, right? Because on the right side, you're always adding positive terms. Here, you subtract sometimes some negative terms. Okay, so this is a bigger summation than this one. So If this one is given, we consider the absolute value. If the absolute value one converges, like this example, we say this original one converges absolutely, meaning not only the alternating one converges, also the absolute value one converges as well. So that's a very strong convergence. So for that reason, we say this guy converges absolutely. Okay. Again, not only the alternating itself converges, also the absolute value series converges as well. Okay, now let's go to the top one. What's the absolute value series of this one? It's sigma 1 over n. How about this one? Does it converge or diverge? Diverges because, again, P series, right? We already talked about this. So this one diverges. How about the alternating series itself? Does that one converges? Again, we already talked about it, right? That one converges by alternating series test. So this is an alternating series for which only the original alternating converges. When you consider the absolute value one, that one diverges. This kind of convergence is called conditionally. Meaning this guy converges only under the condition of being alternating. Like if you remove this condition, it doesn't converge anymore, it diverges. For that reason, this kind of convergence is called conditionally, under the condition of being alternating. So when they're asking about convergency, absolutely drop the negative one. If that one converges, the whole thing, converges absolutely. Let's do another example, the one that we just did. Negative 1 to the n, 2n over n squared plus 1. So the question is, does this one converge absolutely? Absolutely or conditionally? Okay. So what do you guys think? Is it conditionally? Absolutely. Conditionally. Why is that? Because we know itself converges, right? The alternating itself converges. But when you consider the absolute one, which is 2n over n squared plus 1, n squared plus 1, that one diverges. So for that reason, it's called converging conditionally. That will be it. You're going to do the same thing. Basically, that's 10.7. So, and mostly it's part question 1. Question 2 is just bunch of like general series, and I think it's like a overall a question that it doesn't ask you to do certain test. So that's a very good, basically, exercise to do. Okay, we can call it. Anybody is staying for office hours? We can work on problems. On Thursday, we start 10.8 or 10.7 power source. Guys, anybody staying for the office hours? I just want to know if I have to leave my chat open.